Welcome, class. So, have you ever looked at a savings account and wondered how that small amount of money seems to, well, magically grow over time? Or, on a much bigger scale, how a massive corporation decides whether to pour millions of dollars into a new project? Well, the answer to both of those questions, from your personal finances all the way up to the corporate boardroom, really boils down to one single incredibly powerful tool: the compound amount formula. Today, we are going to master this tool. And I don't just mean memorizing it for an exam. We're going to learn it as the fundamental language of financial growth, a language you will be speaking for the rest of your careers. So, here's our game plan for today. We're going to start by getting a real handle on the foundational concept of compounding. Then, we'll meticulously decode the formula itself, taking it apart piece by piece, variable by variable. After that, we'll apply it to a practical business scenario, walk through the actual calculation, and finally, we'll wrap up by discussing the real-world implications and some of those common errors that can completely derail a financial analysis. Okay, let's dive right in. It's been said that Albert Einstein called compounding the eighth wonder of the world. The quote goes, "He who understands it, earns it. He who doesn't, pays it." So let's really unpack why he would say something so powerful about what looks like a simple math concept. It's because compounding is the quiet, absolutely relentless engine behind almost all long-term value creation. To really get this, we first have to separate it from its much simpler cousin, simple interest. Now, with simple interest, the calculation is only on the principal. That's the original chunk of money you invested. So, for example, if you invest $100 at 5% simple interest, you're going to earn exactly $5 in interest every single year. It's linear, it's predictable. But compound interest, that is a whole different animal. You earn interest on the principal and on the accumulated interest from all the previous periods. That $5 you earned in year one, well, in year two, it starts earning interest of its very own. This creates a kind of snowball effect. It means your investment doesn't just grow, it grows at an ever-increasing rate. All right, so how do we precisely calculate this growth? I want you to look at this formula not as some static math problem you have to solve, but as a dynamic model. Think of it like it has a set of levers. As a future manager, as a future analyst, your job is to understand how pulling each of these levers, your initial cash, the interest rate, how often it compounds, and for how long, how all of that affects the final outcome. And here it is. This is our model for the future. A is the final amount. That's the future value we're trying to solve for. P is the principal. That's where we start. Now, this section here in the parentheses, the 1 plus I over n, that represents the growth factor for just a single period. And the exponent, up top, the nt, that tells us just how many of those growth periods are going to happen. You see, every part of this equation tells a piece of a story. The principal, P, is the seed. The growth factor is how much that seed grows each season. And the exponent is simply the number of seasons it has to grow. Let's break down each one of those levers. The principal. This is your foundation. In a business context, this is a huge strategic decision. This is the capital you choose to allocate. Are we going to invest $50,000 in a new marketing campaign, or are we going to invest $500,000? The size of your principal sets the entire scale of your potential outcome. A larger P means that even a small percentage growth results in a much larger absolute dollar return. It is, quite literally, the base of your entire calculation. Now this, class, this is the speed of your growth engine. Think of I as the expected return on your investment. A higher I means faster growth. Now listen up, because here is a critical procedural point that trips up so many students year after year. For our formula to work correctly, this percentage must be converted to a decimal. You just divide by 100. So a 6% annual rate becomes 0.06. A 12% rate becomes 0.12. Forgetting this simple conversion is one of the most common and frankly most costly mistakes in financial modeling, because it will throw your result off by a factor of 100. Okay, now what's really interesting about this next lever is its multiplying effect. N tells us the frequency of the compounding. So let me ask you, which is better, 12% compounded annually or 12% compounded monthly? The answer is monthly. But why? Because when that interest is calculated and added back to the principal more often, you get more periods for your interest to start earning its own interest within a single year. Each period is another cycle of growth, and more cycles means that snowball effect gets a running start, building momentum much, much faster. And this is perhaps the most powerful lever of them all: time. Just look at where t is in our formula. It's in the exponent. And what that means is its effect isn't additive, it's multiplicative, and it's exponential. The longer your investment horizon, the more compounding periods you have, and the more dramatic the growth becomes. especially in those later years. This is exactly why starting to invest early is so absolutely critical, both for a company's long-term projects and, frankly, for your own financial lives. To avoid some really critical errors, you have to perform the calculation in this precise order. Now, it follows standard algebraic rules, but let's just think about it logically for a second. First, you have to figure out the interest rate for a single compounding period. That's your I divided by n. Then you add 1 to it, which represents keeping your original principal plus that new bit of interest for that period. Separately, you figure out the total number of compounding periods over the investment's entire life. That's n times t. Then, you apply that periodic growth across all those periods by using the exponent. And only at the very end, as the final step, do you multiply the whole thing by the initial principal to find the final total value. All right, class, let's move from theory to practice. I want you to imagine your department manager. Your team has done some excellent work, and you find yourself with a $5,000 budget surplus. Now you have an opportunity to invest these funds for 3 years to grow them for a future equipment upgrade you really need. Let's analyze the proposal. Okay, here are the terms on the table. Our principal, P, is that $5,000. The offered annual interest rate, I, is 6%, and what's the first thing we do? We immediately write that down as 0.06. The interest is compounded quarterly, so that means interest is calculated 4 times per year, making our N equal to 4. And the investment term, T, is 3 years. We have all our levers identified. Our job now is to use the formula, project the outcome, and make an informed decision. So now we populate our model. Let's walk through this together step by step, making sure we follow our order of operations meticulously. This is where precision is everything. A misplaced decimal point or a calculator error here isn't just a wrong answer on a test. In the business world, that's a flawed forecast that could cost real money. So we substitute our values directly into the formula. A equals our principal of $5,000 multiplied by, the quantity of 1 plus our annual rate, 0.06, divided by the number of compounding periods, which is 4. This entire quantity is then raised to the power of 4 periods per year times 3 years. Let's simplify this. Inside the parentheses, 0.06 divided by 4 gives us 0.015. Add 1, and our growth factor for each quarter is 1.015. Now for the exponent. 4 times 3 gives us 12 total compounding periods. So the equation now becomes A equals 5,000 times 1.015 to the 12th power. And this brilliantly illustrates the result. After 3 years, our initial $5,000 has grown to $5,970.25. Now, this isn't just a number. This is a tangible outcome. You can now go to your director and state with absolute confidence, if we invest this $5,000 surplus under these terms, I project it will become nearly $6,000 in 3 years. This is going to generate an additional $970.25 for our department's future initiatives, effectively for free. See? That's how you turn a calculation into a compelling business case. So the crucial point here is that getting the right number is really only half the battle. You also have to understand what that number actually means for the business. And just as importantly, you have to know how to arrive at that number reliably, avoiding the simple mistakes that can undermine your entire analysis. You are going to use this logic constantly. For capital budgeting, you'll use it to decide if buying a new $1 million machine will generate enough future value to be worth it. When you're evaluating project ROI, return on investment, you'll compare multiple projects to see which one grows the company's capital most effectively. This whole concept is the bedrock of corporate financial planning. It dictates how loans are structured, and if you ever go into wealth management, it is the core principle you will use to advise your clients. Now, these might seem like small academic errors right now, but in the business world, their consequences are severe. Forget to convert 6% to 0.06, and you'll project a return that is 100 times too large. That's a catastrophic error. Use the wrong order of operations, your result is meaningless. Mismatching time units, say using a monthly interest rate with T in years without adjusting, will completely invalidate your forecast. These are not just math mistakes, they are costly business miscalculations that lead to poor strategic decisions. Precision is absolutely paramount. I'll leave you with that thought. We just saw a nearly 20% return in only 3 years. So what happens when the time variable T isn't 3, but 30 or 40? What happens when the principal isn't just a $5,000 surplus, but the annual profits of an entire company being reinvested year after year after year? The numbers. They become almost unimaginably large. the principles we discussed today, those levers of principal, rate, frequency, and time, they don't just apply to one business problem. They apply to a lifetime of value creation. Master this, and you've mastered a fundamental law of financial growth.